Good afternoon, everyone. My name is Alan Vertigrall. I am an independent mathematics researcher. Today, I am offering the first in a series of lectures on orbit theory of natural numbers. This lecture is on the primality of numbers, in particular, the natural numbers n-1, n, and n+1. These are the counting numbers, 1, 2, 3, 4, all the way out to infinity. The whole numbers, no fractions, decimals, negative numbers, imaginary transcendental numbers are used. Not even zero is defined. The domain is only the natural numbers. By the end of this lecture, you'll understand that the natural number n knows the primality of n-1 and n+1 without even checking them. This is a novel concept in mathematics. Given an arbitrary number n, there are no current methods that determine if n+1 is a prime number simply from examining n. We can factor n into its prime factors, yet adding 1 to that product of primes tells us little about whether n+1 is prime or composite. Current methods require that n+1 be factored before deciding if it is a prime number. Recently, I presented this paper to the Math Computer Science Engineering Conference, MATHCS 2024, held in Dubai, United Arab Emirates on December 28th and 29th of 2024. It is on determining the primality of n-1 and n+1 solely based upon examining the structure of the natural number n. This lecture discusses some of the results of the research that I did during 2022 and 2023. Let's begin. Primality is defined simply as determining if a number is either a prime or composite. The methods presented in the paper show how primality can be determined without using factorization or sieving, the classical ways of determining if a number is prime, or even using multiplication or division in determining if a number is prime. Primality can be determined simply using modular addition. Math theory starts off very simply. All of us know that numbers are put on a number line. It is the first concept that we learn in school at the earliest age, even before we learn how to add and subtract. Numbers follow each other one by one on the number line, spaced separately by 1 unit. I propose that we look at numbers not on a line, but as distinct entities within themselves. We can do this by visualizing a circle surrounded by any number of points. Number them from 1 to n. This circle is a representation of a natural number. So consider the number n equals 5. The circle representation of number 5 is shown here, a circle with 5 dots labeled from 1 to 5. This concept leads to new properties of numbers that define primes and composites in ways different than what we learned from grade school onward. Let's play a child's game of counting around one of these circles. So let's choose 1 as the starting point. Going from the starting point, count increments of 1 and list the sequence of numbers as we encounter them by counting this increment. And we get this row, 2, 3, 4, 5, 1. And that's the sequence for the increment 1. If we then count by 2, we get the next row, 3, 5, 2, 4, 1. And if we count by 3, we get the third row, 4, 2, 5, 3, 1. And if we count by 4, we get the next row. So we're going 5, 4, 3, 2, 1. And the last row will always be ones. We could have listed these sequence members in columns rather than rows, and thus the last member is always going to be the same because we are always returning to the starting point. We now have a set of sequences for this number 5 in an n by n array. We can do this for any number. These sequences are a representation of the number 5, just like the circle is a representation of the number 5, or even the symbol 5 is a representation of the number 5. Notice the column to the right. I will mention it here, but this will not be included in this lecture. This value is the orbit value of each of the rows. An orbit value is the number of times we have to go around the circle based on an increment before returning to the starting point. I will discuss orbit values extensively in future lectures, since it is at the core of what is called the orbit theory of natural numbers. Let's first understand when a number n is prime or composite. Examine the array that has been created. Let's first get rid of these ones in yellow. Let's just toss them out. They're always going to be ones, and they are not necessary at this point in time. But I assure you, ones will reappear shortly and become the very key to this part of orbit theory. So let's focus on the smaller array with the numbers in white. This set of numbers is called a Latin square, originally identified by Leonhard Euler in the 1700s, and is used extensively in other branches of science to determine optimal testing strategies when multiple factors are involved. They are called Latin squares because Euler originally used Latin symbols rather than numbers. A Latin square is where each number or symbol appears only once in each row column. If you look, you can see that each member of this particular array meets this criterion. Look at each of the 5s. Each is unique for its own row column location. These arrays can get quite big very fast since this is an exponential function. Mathematically, one can conceive of a Latin square that has more cells than there are atoms in the universe. That is a lot of numbers. We don't have to deal with these numbers. We can let computers do that for us. Let computer programs search for patterns in these square arrays. When I first started, I used a spreadsheet application to study the first 108 natural numbers. It is easy to set up a spreadsheet that creates these arrays, some which are for prime numbers and some which are composites. It is actually pretty fascinating to see a 100 by 100 array update its 10,000 cells in a blink of an eye. This is the power we have today using computers to examine large sets of numbers. Let a computer application or program handle the counting of the increments around the circle and recording the sequences. Actually, there is an easy construction rule that can be programmed to create and analyze these arrays. The construction rule is simple. First, create a single row array called the additive increment array from 1 to n minus 1. Then initialize the first row of the array to have consecutive sequence numbers from 2 to n. Add these two together cell by cell to get the second row. Add the increment array to that row to get the third row, and so forth. We can continue in this manner for all the rest of the rows, and we come up with this square array. We denote these arrays by square SQ of n, or simply SQ of n. Once created, it turns out that if the square SQ of n is a Latin square, then n is a prime number. Likewise, if n is a prime number, then the square SQ of n is going to be a Latin square. If it is not a Latin square, then n is a composite number. This example for square of 13 is a Latin square. Notice that there are no ones in any of the cells. The ones are still missing. We can augment our concept of a prime number a little further. When using the construction rule, if no ones are present in square SQ of n, then n is a prime number. If ones are present, then n is a composite number. Let's look at a couple of examples of composite numbers. On the left is the square SQ of 14, where n equals 14. On the right is the square SQ of 15, where n equals 15. Notice the pattern of ones in each of these. If n is a composite number, then a specific pattern of ones appears in the array. The left array for n equals 14 has the distinguishing cross that is found for all even numbers. The right array for n equals 15 has ones in a pattern that's spread out into the 4 quadrants. Here are some other squares SQ of n for n equals 8, 9, 10, 11, and 12. As expected for n equals 11, the square SQ of 11 has no pattern of ones since 11 is prime. But just notice the pattern of ones in the others. That pattern is unique for that particular number. These squares for both prime and composite numbers have some interesting symmetry properties. The squares are always symmetric on both diagonals. We can fold the square on its diagonal and the numbers match up. This example is for SQ11. Notice that the numbers mirror each other on either side of the diagonal. So if we fold here, this 11 will match this 11, and these two 10s will match these two 10s, and all the numbers on this side will be matching the same numbers on the other side. This is true for the main diagonal from the upper left to the lower right. It is also true for the other diagonal from the lower left to the upper right. The numbers match up when folded. This 2 matches with this 2, and these two 3s match with these two 3s, and all these numbers on this side match to the same numbers on the other side. If we fold the square on its horizontal and vertical center lines, the numbers do not match up. If we fold on the x-axis, 11 down here does not match with 2 up here. The same thing if we fold on the vertical axis, 2 doesn't match with 11. None of these numbers match with those numbers on the other side. However, the pattern of ones for composite numbers are symmetric on the xy axis. The ones form an invariant group regarding composite squares. We can fold, turn, flip, go on the diagonals, do pretty much anything we want with this, and the pattern of ones will never change. Visually, this is interesting since the ones seem to be totally independent of all the other numbers. This allows for some novel strategies for testing primality of a number n. The first testing strategy is simply the Latin square test. We can test each cell to see if its member is unique to its row column. If all the cells have this property, then SQ of n is a Latin square and n is a prime number. Yet this is a lot of cells to check, especially if the squares are quite large for numbers into like the trillions and beyond. Even for a computer, that's a lot of cells, to test, and it could take hours, to determine if a number is prime doing this. Fortunately, because of the symmetry properties, we can drastically cut down on the number of cells that need to be tested. What are we testing for? A cell with a value of 1. Of course, we have to determine the value in that cell. Yet we are only using addition, and computers love to add more than any other type of operation. Then we can test that value to see if it is equal to 1. A computer can do this very quickly. If even a single 1 is found, we know this number n is a composite number. Because of the mirroring effect of the symmetry along one of the diagonals, we can cut the number of cells to be checked in half. And because of the symmetry of the other diagonal, the computer only needs to check 1/4 of the values. And so it's really this section that needs to be checked. But because of the symmetry along the XY center lines for the cells having the pattern of 1s, the area to be checked is reduced to 1/8. We just have to check this particular sector in order to determine if a number is prime or composite. Now, if we look at that sector, we don't have to check all the values, because we know by the definition of the construction rule, there will never be a 1 in these yellow cells. So we can concentrate simply on the portion of the sector that's in white. An algorithm can be created called the temple search because it looks similar to a Mayan temple from the side. It uses 2 indexes, one for the row and one for the column. The algorithm uses an algebraic expression to determine the value of a particular cell. Then that sequence member can be checked to see if its value is equal to 1. If anyone wants a challenging algebra problem, devise this formula that traverses the triangular cells and determine the value. The result is published in the first volume of the Orbit Theory of Natural Numbers, subtitled Fundamentals, that is listed in the references at the end of this lecture. The code for the temple search algorithm is found on my GitHub library listing in the references also. The search is definitely faster than checking the entire square SQ of n to see if it's a Latin square. However, this is still a fair number of cells to test for very large numbers. Another interesting property revealed itself during the research and is known as the staircase conjecture, shown as the green region in this square SQ of 21. It seems that there's always a 1 found either on the main diagonal or the diagonal below the main one. It has been demonstrated that this holds for all prime composite numbers up through 1 million. Searching for 1s in this manner is known as the staircase search, because it walks up the stairs of the staircase. If it gets to the top without finding a 1, then n is a prime number. Using this search pattern, the largest prime identified that I have found is around 4.2 billion. And it does it in about 60 seconds on my laptop with an Intel Core i7 processor. Of course, it finds composite numbers in a fraction of the time, since as soon as it finds a one, and uh, n is determined to be a composite number. So we have this algorithm, and it walks up, and if any of these cells have a one in it, we know right away it's a composite number. The algorithm for the staircase search is referenced as a C++ program in the GitHub location and is freely available for testing and use by anybody. It is fairly straightforward and easy to code. It uses a single index to climb up the stairs. You can see that is simply calculating a cell value and then testing that value to see if it's one. The algebraic expression is also derived in volume 1 of the orbit theory books. So we have a way of testing a number n to see if it's prime or composite. Now that the basic theory has been presented, we can explore some fundamental questions about numbers. We can tell from the square SQ of n itself whether n is prime or composite using the staircase search. A more interesting question is this: when is a natural number preceded by a prime or composite, and when is it followed by a prime or composite? These questions actually reduce to understanding how the sequences of one square convert into those of the next square. Spoiler alert, the number n knows that n minus 1 and n plus 1 are either prime or composite without examining n minus 1 or n plus 1. Every number n knows the primality state of where it has come from and where it is going. Mathematically, this is very beautiful. So how does this happen? You saw the pattern of ones that occur for composite numbers and the lack of any pattern for prime numbers. These patterns for n minus 1 and n plus 1 and the lack of the pattern actually show up in the square SQ of n. The shadows from the patterns of ones show up in the square of n. How do these sequences change from one number to the next when adding or subtracting 1 from n? Understanding this will tell us how n knows the primality of its two immediate neighbors. Here's a visual set of squares, SQ of n, from n equals 8 to n equals 12. Notice the different patterns, and notice that n equals 11 has no pattern of ones. How do the sequences from one of these squares transform into sequences of the next in line? The submitted paper shows how this is done. It defines rules for converting from one to the next or from the current to the previous set of sequences. These rules are called the forward transformation rule and the reverse transformation rule. So before getting into seeing these patterns, we have to define something called the zone. And this figure shows various zones. A zone is created when counting passes one without landing on it. So a zone is equivalent to an orbit. In other words, it's how many times around the circle one goes before one reaches back to one. Now remember, we threw away the one at the end. So we're only looking at the sequences of numbers up through to the point where we actually land on one. So in this case, looking at a single row for n equals 15 with the increment d equals 4, we get 4 zones: 5, 9, 13, 2, 6, 10, 14, 3, 2, 3, 7, 11, 15, and 4, 8, 12. Notice again that a new zone is entered when the number drops to a lesser value. So these are increasing, and that drops to 2, which increases and drops to 3, and increases and drops to 4. So there are 4 zones here before it lands on 1. So We can number zones in order, 1, 2, 3, 4, all the way down to n minus 1. And so zone 1 only has one orbit. Zone 2 has two orbits. Zone 3 has three orbits. Zone 4 has four orbits. Remember now, when I'm referring it to in this way, I'm looking across the row at all the different zones. So the first row you see has no zones. The second row has two zones, green and blue, and the third row has green, blue, and yellow. So that's what is meant by this slide. So transforming sequences from square S cube n to square S cube n plus 1. We have 11, and we want to convert those sequences to the square SQ12, which has a pattern of ones. So there's no pattern of ones in SQ11, but somehow when we add 1 to n, we suddenly have a pattern of ones appearing. So I want to define a new term, square of nr, which is basically r is the row for the square of n. And I want to actually be looking at uh, two rows. We can look at this fourth row over here and the fourth row over on the right. So let's put them on top of each other, and we can then see very clearly what is happening. So for zone 1, nothing needs to be done because they're going to be the same numbers in both zones. Zone 2, it seems like we subtract 1 from the member number. So 1 from 2 is 1, 1 from 6 is 5, 1 from 10 is 9. Same thing over here. But now that it's zone 3, looks like we're subtracting 2. 2 from 3 is 1, 2 from 7 is 5, 2 from 11 is 9. And for zone 4, we're subtracting 3. 3 from 4 is 1, 3 from 8 is 5, and for the last zone 5, we're subtracting 4. And again, if we look here at a different row, the sixth row of both square of 11 and square of 12, we see again zones 1, we don't subtract anything. Zone 2, we subtract 1. Zone 3, we subtract 2. Zone 4, we subtract 3. Zone 5, we subtract 4. 6, we subtract 5. 7, we subtract 6. So we can define a rule, and this is called the forward transformation rule. To convert the sequences of square SQ of 11 into SQ of 12, subtract from each member one less than the zone number, and apply any modular adjustments for the modulus 12, which is the modulus that we're going to. So going back again, we're subtracting 1 less than the zone number on every row in order to derive the sequences for the next row. And notice this bottom one here. We're going from it's row 6, and so we subtract 1 from each of the zones, and then subtract that from the member values for square of 11 on the 6th row. We actually get this repeating pattern of 7, 1, 7, 1, 7, 1, 7, 1, 7, 1, 7. So ones are showing up, even though there's only one 1 here, and um, none there. The only reason we put the number here, 1 here, is that it is the last cell. And remember, we've gotten rid of ones, but in order to make the number of cells between these two sets of sequences the same, we have to actually add that one back in. And then we can actually subtract its zone number, -1, from it, and applying the modulus for 11, I mean for 12. So we get, um, we end up with the number 7. So when is n+1 prime or composite? It's when the shadow of the pattern for n+1 is found in n. So we have a pattern of ones here. That's where we're going to, but are they showing up here? There are no ones showing up in this square. But notice the numbers in bold. That is the pattern that is there. And so there must be a mapping from this particular pattern of numbers in bold to the numbers in n equals 12 that become 1. So, the rule ends up being simple. If we're in zone 2, and if a 2 exists in this blue zone, then it'll convert into a 1, because remember, we're subtracting 1 to get the next number in the sequence for n equals 12. So if a 2 shows up, it's going to become a 1. So we can just look for 2s in zone 2, and we'll know that the following number is going to be composite. And this also applies for zone 3. If there are 3s in zone 3, remember we're subtracting the zone number -1, which would be 2. 2 from 3 is 1, and that then shows up for those particular numbers. And the same thing with each of the zone, even all the way down to zone 7, where there are 2 7s present that will convert to 1s, because zone 7 -1 is 6, and then 6 from the 7 that's present here will give us these 2 1s over here. So we see there's a mapping from these numbers to the pattern of 1s. And there's a rule that we can apply that is simply, first of all, ignore zone 1, because there will never be 1s in either of them. If there's a 2 in zone 2, it transforms to a 1. If there's a 3 in zone 3, it transforms to a 1, etc. So we can see the pattern without looking at the next number. So when is n+1 prime or composite? It's when the shadow of the pattern for n+1 is found in n. And I've explained how that can occur, how that we can actually see that and test for it, very simply. So the pattern of ones, or lack of pattern, of the preceding square SQ of n shows up in the square that follows it. If we want to see the pattern of ones for n+1, we only need to look for the pattern in the square SQ of n. In this case, we're not looking for ones, but looking for numbers that will transform into ones in the next square. On the right is the pattern for n equals 12. On the left, you can see in boldface, again, more clearly, that these numbers are the ones that when the rule is applied, the forward transformation rule, they convert to ones in the subsequent set of sequences. So how about the reverse direction? Transforming sequences of the square SQ of n to SQ n-1. So we're going in reverse. And in this case, um, we're going from SQ12 to SQ11. These sequences are going to be converted into these sequences. This pattern of ones will disappear after that reverse transformation method is done. So if we do this again, we can choose a row 6 for each of them. And remember, row 6, it was 7171, 71717. And then row 6 for SQ of 11 doesn't have any ones. So how do they disappear? Well, we compare the two. We can see that the first zone, again, um, nothing happens. We have 0. Whether we subtract or add it, we don't know yet. Now, for zone 2, we have a 1, and the difference between the two is a 1. So it looks like we're adding 1 to 1 to get 2. And in this case, 1 to 7 gives us 8. Now we go to the next zone. It looks like the difference is 2. 2 plus 1 is 3. 2 plus 7 is 9. Zone 4, 3 plus 1 is 4. 3 plus 7 is 10. Zone 5, 4 plus 1 is 5. 4 plus 11, 4 plus 7 is 11. And the final one, 5 plus 1 is 6. And we don't need to concern ourselves with the last cell because it's out of the bounds of the smaller number n. So we can formulate a rule, the reverse transformation rule. It looks like we are going to add 1 less than the zone number. So 1 less than the zone 2 is a 1. 1 less than zone 3 is a 2. 1 less than zone 4 is 3, etc. So we can define this reverse transformation rule to convert the sequences for a square SQ of 12 into SQ of 11, add to each member 1 less than the zone number, and apply any modular adjustments for the modulus 11. So when is n minus 1 prime or composite? It's when the shadow of the pattern for n minus 1 is found in n. When is n minus 1 prime or composite? It's when the shadow of the pattern for n minus 1 is found in n. So this is when the pattern is going to convert into ones using the reverse transformation rule. So you can see the pattern of numbers here that are in boldface. Those are the ones that, when we go in reverse, will end up being ones in this direction. Or you could say that if we're going using the forward transformation rule, they're going from 1 to a different number here. But let's stick with the reverse transformation rule. And let's see if we can come up with a rule. First of all, we want to ignore this last column and row since they're going to be out of bounds. So we're not going to look at any of those numbers in this. Then notice that this 10 is one of those numbers that converts into a 1, going in reverse. So we can formulate a rule that this is n equals 10. So if a 10 shows up in zone 1, then it's going to convert into a 1. And in the blue zone, zone 2, if 9 shows up in the blue zone, zone 2, those are converting into a 1. And there are in zone 3, if an 8 shows up in zone 3, and there are no zones in this yellow portion, so we can ignore that. In zone 4, if a 7 shows up, then it's going to convert into that final one, and the rest, have uh, no thing. So what is the rule? If n shows up in zone 1, then we have a 1. If n minus 1 shows up in zone 2, if n minus 3 uh, shows up in zone 4, then it'll convert into 1. So basically, if n minus alpha shows up in zone alpha plus 1, then it came from a 1. So yeah, let's test that out. Well, if alpha is 0, then zone 1 would need to have an n. And um, if alpha is 1, then that would be zone 2, and it would need to have n minus 1, or in this case, a 9. So we have a rule where we can examine n, which is n equals 10, for these numbers. 10 in zone 1, 9 in zone 2, etc. And if we can show that none of these numbers show up, then we can be assured that the number prior is going to be a prime number. So the natural number n knows whether n minus 1 or n plus 1 are either prime or composite. Again, if there was none of these numbers present that follow the rules that I just explained, then there won't be a pattern of ones over here in the preceding number, and that would mean that the preceding number is prime. So for m plus 1, to determine primality by examining SQN, we actually have some more powerful conjectures that seem to apply. Zone, the zone conjecture for composite numbers m plus 1. All composite numbers n plus 1 have at least 1, 2 in zone 2 of square SQN. So there should be at least 1, 2 if it's a composite number. In all the composite numbers will have a 2 in zone 2. And the uh, corollary conjecture for a prime number, n plus 1, all prime numbers n plus 1 do not have a 2 in zone 2. And so the conjecture basically states that we only need to look at zone 2 to determine if the number n plus 1 is prime or composite. If a 2 exists in zone 2, then that number n plus 1 is going to be composite. And if there are no 2's, then n plus 1 is going to be prime. So we've simplified it down to just examining a single zone in order to determine if n plus 1 or n plus 2, n plus 1 is prime or composite. Now let's consider n minus 1. To determine primality by examining SQN, we only need to look at zone 1 of the square SQN. And if it has a value with the member n, then n minus 1 is composite. And if it doesn't have a value of n in zone 1, then n minus 1 is prime. So these are several powerful conjectures that really simplify determining primality with the minimum number of checks. I mean, it's still going to be a large amount of checks for very, very large numbers, but the fact that we only have to search for certain numbers, then uh, it actually can be very quick, definitely quicker than some of the other tests that uh, need to get done. So this slide shows the same square across the top for n equals 9. Below it are the squares for the numbers n equals 8 and 9 and 10. And notice there are patterns for 8, 9, and 10 of 1, since all those numbers are composite numbers. And they're going to show up in n equals 9. Definitely the ones, down here, show up there because it's the same square, SQ of 9. And if we look at this, the preceding number, its pattern shows up also, but not as ones, but following the rules. If n shows up in zone 1, in other words, if 9 shows up in zone 1, it's going to convert into 1. So we can just check there, and indeed, 9s exist, and we know that there are the n equals 8 is a composite number. And the same thing over here, this cross, we only need to look for a 2 in zone 2, and there are 2 of them, and those are the first 2 ones over here. And therefore we can conclude that n equals 10 is going to be a composite number. We have seen how, starting with the number line, we can create these unique entities, circle surrounded by a set of points, and number them from 1 to n. And these represent each number separately as unique entities. And by using a child's game best left to computers, we can generate a set of distinct sequences that we put into these square arrays. We can determine the primality of any one of these numbers just by searching for ones within a small section of the array. We can also look for shadow patterns for n minus 1 and n plus 1 to determine their primality without even examining n minus 1 or n plus 1. Now, the paper that was submitted at the conference reports on just the last major finding of a 2-year project, and this was basically the results. The n knows the primality of its 2 neighbors. But remember, at the very beginning, I showed that each row of sequences has what is called an orbit value. So here's an orbit value for the square n equals n of 13. For each of the rows that are listed in here. And this is the orbit value, how many times around the circle it must go before it comes back to the starting point. Now we can take these orbit values and put them in a column, with the number at the top, and then put those columns together into a table. And this generates what is called the orbit table. The orbit value table has remarkable structures within it that determine primality of numbers in a totally different way, as well as identify specific mathematical structures relevant to a number of the unproven conjectures in number theory. Its beauty astounds me, which led me to my 2-year research project. My research is published in the 3-volume work called Orbit Theory of Natural Numbers. The first volume is on fundamentals and is available on Amazon print on demand. The second volume is on applications to number theory, also on Amazon. The third volume is simply a listing of over 100 C++ programs I use to analyze squares in the orbit table. The first 2 volumes are large print, 8 by and a half by 11. And it's full color to bring out the various structures. And, and total close to 600 pages of research results. The fourth book presents basically the theory that I've described here today, because that was a finding that came about after these 3 volumes had gone to press. And listing 5 is so you can download the paper that I submitted from the math conference proceedings. And number 6 here is my GitHub location, where I have public accessible C++ programs for the temple search and the staircase search, as well as searching for of using the rules to search for whether or not the number preceding or the number after are prime or composite, just by searching for the patterns within number 1. Here's my email address. If you have any questions, feel free to email me and I'll respond as best as I can. So that's it. Thank you for bearing with this lecture. It's, I believe, a fantastic discovery in mathematics, because prior to this, no mathematician would be able to say that just by looking at n and what we know about n, that we can tell whether or not that all numbers that follow n or all numbers that precede n are prime or composite. We can definitely do a lot of numbers if we know that n is odd. We know that 1 plus n is going to be an even number, but there's no general rule for all numbers up until this point, where we can look at the square structure of the number n and then look for the shadow patterns and determine the primality without even checking its neighbors. So thank you very much.